Welcome back to number theory. So today I'm going to be talking about modular arithmetic. So yeah, I think I'll just define it and kind of give some examples and whatnot, and it should be good. So maybe I'll just start off with the idea. So kind of the idea is you can simplify arithmetic. I don't want to say simplify, but I mean, yeah, simplify. So probably a classical example I talked about when we talked about rings was Z mod 2Z. And we'll talk about what this actually means. And basically, what this means, if you recall, this was a ring and it had a multiplication and a addition law, and it looked like this. So how can we kind of interpret what this means in terms of Z mod 2Z? Well, draw this box again, but rather than using 0 and 1, I'm going to put in even and odd. So what this is saying, if we just, everywhere where we see a 0, we put an even, and wherever we see a 1, if we put an odd, what do these two tables actually say? What these tables are actually saying is if I take an even number and an even number and add them together, it's going to be even. Similarly, if I add an even and odd, it's going to be odd, and an odd is even. Multiply an even by an odd, we get an even. Multiply an even by an even, we get an even. Multiply an odd by an odd, we get an odd number. So that's kind of one way we can interpret this table. And we'll actually view this as so-called residue classes. So the idea is if we pick an integer 2, or in this case it's 2, but you pick an integer n, and you create an equivalence relation on the integers by a is equivalent to b if n divides a minus b. So what does this mean? So the way I like to think of equivalence relations is you have a bunch of things and you're just putting them in boxes. So for example, for n equals 2, we have the a is equivalent to b if a and b are both odd, or a and b are both even. So, and you could ask, what does odd and even mean? Odd just means you're of the form 2n plus 1 for some n. Even is you're of the form 2n. And yeah, this gives us the equivalence classes are going to be odd and even numbers. So first, let's actually show that a equivalent to b if n divides a minus b is an equivalence relation. And so what that means is we have to check that a is equivalent to a. We need to check that if a is equivalent to b, this implies b is equivalent to a. So this is called reflexivity. So it's reflexive. This is called symmetric. And then if a is equivalent to b and b is equivalent to c, this should imply a is equivalent to c. So this is called transitive. And so if we take a equivalent to a, so we note that n divides 0, So n divides a minus a. So that implies a is equivalent to a for every element a. For symmetric, if n divides a minus b, then a minus b is equal to nk. So b minus a is minus nk. So n divides b minus a. So that tells us that a equivalent to b implies b is equivalent to a. So we are symmetric, and now for transitive, we have if a is equivalent to b, that means we have n divides a minus b, and so we can write a minus b is n times k. And similarly, if b is equivalent to c, then n divides c minus b. So c minus b is n times l for some l. So here we have k and l are in the integers. So what we can do is if we subtract these two equations, this is going to give us a minus c is nk minus nl, which is n k minus l. So this implies a is equivalent to c. So this is an equivalence relation. So we have that this division forms an equivalence relation, and then the residue classes are the equivalence classes of the relation. So the residue class of A mod n is the equivalence class of the above relation. I probably should say equivalence relation. So going back to our example of z mod 2z, our equivalence classes, are you divisible by 2, or do you have remainder 1? So are you odd and even? So maybe an example is if we look at in z mod 2z, the equivalence class of 2 is equal to the set of evens, and the equivalence class of, say, 5 is the set of odds. And so now we can talk about a system of representatives. So a system of representatives is a subset of z such, so maybe I should call this subset something, say x, a subset of z, such that every equivalence class has exactly one element of the class in X. So going back to the example of z mod 2z, so we have that 2 and 5 is a system of representatives for z mod 2z. So that's an example. Maybe let's also look at z mod 3z. So if we look at z mod 3z, what happens now is if you look at the condition that we have a is equivalent to b if 3 divides a minus b. And so what are the options here? Well, I'm going to claim that 0, 1, and 2 is a system of representatives. And kind of one way to see this is if you look at this notion that 3 divides a minus b, that's the same as saying a and b have the same remainder when divided by 3. So maybe let's prove that. So there are n equivalence classes in Z mod NZ. So here, and maybe I'll also say, and 0, 1 to n minus 1 is a system of representatives. So let's do this. So first, let's note that 0, 1 to n minus 1. We'll note none are equivalent to one another. And to see this, we'll just say if we have A and B are in the set 0 to n minus 1, and say A is not equal to B, then if we look at A minus B, well, what is the most A minus B could be? A minus B, at most, it can be n minus 1. So it's strictly less than n. And the least it could be is negative n minus 1. So we have that A minus B is between negative n and n. So the only way n divides A minus B, since there's no integer between 0 and 1, is if A minus B is equal to 0. So we see that we see that if A is not equal to B, then A is not related to B. So each of these is a distinct, has a distinct equivalence class. So this also tells us that there are at least n equivalence classes. So we found n different elements, none of which is equivalent to one another. But now, so we have that there are at least n equivalence classes, but now we need to show that we have at most n equivalence classes. And to do that, if we take, so just pick some element, say x in the integers, right? If I can show x is equivalent to some y, x is equivalent to some y that's in the set 0 to n minus 1, then every equivalence class is given by one of the 0 to n minus 1, so they will also be a system of representatives. So to do this, we'll just use the division algorithm, and that says that x is nq plus r, with r between 0 and n. So if we take, so r is in the set x, which was the set 0 to n minus 1. Namely, x minus r is nq, so x is related to r, which is in the set x. Thus, we have that every integer is related to some element in the set 0 to 1 to n minus 1, and namely, this forms a system of representatives for z mod nz. So here we have that z mod 3z, a is equivalent to b if 3 divides a minus b, and we have 0, 1, 2 is a system of representatives. But there's something more that's going on here, because this, so far we just have a set, right? But up here at the very top, when we talked about z mod 2z, we also had an addition and a multiplication. So this suggests we can put a ring structure on z mod nz. And yeah, so maybe let's do the example with z mod 3z. So if we look, we'll take plus. We know 0, 1, and 2 is a system of representatives. And the table looks as follows for addition and multiplication. And you can see, you could go ahead and check that this actually forms a ring structure. And the kind of the way you do this is, for example, if we do 1 plus 1, well, since this is a system of representatives, 1 plus 1 is 2, so we get 2. But if we look at 2 plus 2, 2 plus 2 is 4. But modulo 3, it is 1. That is, when we take the remainder when divided by 3, we get 1. Because that's an element of our system of distinct representatives. Similarly, here, the zeros, that just says if you multiply anything by a multiple of 3, you get a multiple of 3. But the multiplication is a bit trickier to see. So, yeah, we will, let's go ahead and show that, so kind of the way it works is the same, that you could just do this with the system of representatives. So if you take 2 and 2, multiply them together, you get 4. Its remainder is 1. So here is kind of the proposition. Addition and multiplication are well defined on z mod nz. And kind of the way we did it up here was we used 0 to n minus 1. But in general, since we're dealing with equivalence classes, we need to show that we can take any equivalent things. So kind of the proof is say a is equivalent to a prime and b is equivalent to b prime. This is modulo n. We want to show that a plus b is equivalent to a prime plus b prime, and a times b is equivalent to a prime times b prime. So this tells us that our addition and multiplication are well-defined operations. So to do this, we note a minus a prime, it's going to be n times k. B minus b prime is n times l for some k and l in the integers. So if we just add these two equations together, we get a plus b minus a prime plus b prime is equal to n times k plus l. So this tells us that a plus b is equivalent to a prime plus b prime. So that's how we get that addition is well defined. As for multiplication, what we do is we have that a minus a prime is nk. So I'm going to write this as a is equal to a prime plus nk, and b is b prime plus n times l. Now I'm going to multiply these two equations together, and I'm going to get a times b is equal to a prime plus nk times b prime plus n times l. And if we multiply this out, we're going a prime times b prime plus nkb prime plus nla prime plus n squared kl. But if we see what this is just a prime b prime, and we can factor out this n. And moving the a prime and b prime to the other side, we see that this tells us that n divides ab minus a prime b prime. So ab is equivalent to a prime times b prime. So we have the addition and multiplication are well defined. And if you go to the other ring axioms, like the units and all of that, everything from there just follows from the fact that the integers are a ring. So this gives us a ring structure on the integers modulo 3, or modulo n for any n. Now, I want to do one more example that kind of show, or let's do two more examples. So let's do z mod 4z. So if we think of addition, 0, 1, 2, 3, 0, 1, 2, 3. So 0, 1, 2, 3, 0, 1, 2, 3, 2, 3, 3, 0, 0, 0, 1, 1, 2. So that's the addition table. And then if we look at the multiplication table, we're going to notice something strange happens. So we have all the zeros here. 3 times 3 is 1. 3 times 2 is 2. So the strange thing in this multiplication table is if we notice 2 multiplied by 2 is 4. So which is 0. So we have two non-zero things multiplying to get something that is 0, which is a bit strange. Also, if we look at 2 times 3, that's 6, which is 2 mod 4. We have something that's not 1 multiplying with something. So here we have 2 times 2 is 0 mod 4, which is strange because neither of these are 0. And we also have 2 times 3 is 2 mod 4. And this is strange because 3 is not 1. So this kind of is a strange phenomenon. And one might add, if one compares it to the table for z mod 3z, you notice that after you look at the zeros, this phenomenon doesn't happen. The only way x times y equals y is if x is equal to 1. So I'm going to define something. A zero divisor is some element not equal to 0, such that there exists some b with a times b equal to 0. So here, 2 is a zero divisor. And I'm also going to define a field is a ring with no zero divisors. And if I want to be specific, I should say it's a commutative ring. Otherwise, it's just a division ring. So, yeah. This kind of prompts the question as to when do zero divisors exist, and when do they not? And we should note, so this usually isn't the classical definition of a field. So classically, a field is a ring such that for every x not equal to 0, there exists some y with x times y equal to 1. And let's just do the proposition that the field definitions are equivalent. Are they? I think so. At least for the integers, they should be equivalent. Yeah, so maybe I shouldn't have this definition here. So I should say a field has no zero divisors. So if we prove this, so assume for sake of contradiction that we have a field with some zero divisor, a zero divisor. So we know that we have that there x times y is equal to 1 and x times z is 0 for some y and z in the ring R. So what we could do is if we add these together, we get x times y plus z is equal to 1, right? So here we're going to have z is not equal to 0, right? So if we have some zero divisor, we have x and y that satisfies these, and z is not equal to 0. So since we're a field, we have that there's some w in the ring with z times w is equal to 1, right? So if we consider xz is equal to 0, but if we look at xz times yw, this is xy times zw, which is just 1 times 1, so it's 1. But that tells us that 0 times xw is 1, which would tell us 0 is equal to 1. And that's not the case. So this is the contradiction. Because 0 times anything is 0. So you can't have zero divisors in a field. So, yeah. A question we could ask is, when do we have zero divisors? and or namely just when is here's kind of the question: when is Z mod NZ a field? So something we could note: what goes wrong here when we were looking at Z mod 4Z? We had 2 times 2 is equivalent to 0 mod 4. Well, 4, factors as 2 times 2. So that's one issue that can come up. So if n is not prime, Z mod NZ is not a field. So the proof of this is rather simple. If you can write n as a times b with a and b less than n. So if we look at a times b, this will be 0 modulo n, and these are also greater than 1. So Z mod NZ has 0 divisors and is not a field. So if we're not prime, we're not a field. So that just leaves us to the case that when we are prime, and we'll get to that later. So we will show later that if n is prime, then Z mod NZ is a field. So yeah, to get to that, there is one last thing I kind of want to talk about, and it's the notion of a unit. A unit in Z mod NZ is some x not equal to 0, such that there exists some y in Z mod NZ with x times y equivalent to 1 modulo n. So and this is actually, if we can figure out what the units are, that's actually a good criterion. Because if you look at the field, definition of a field is a ring such that every non-zero element's a unit. So here is the proposition that classifies the units. An element in Z mod NZ is a unit if and only if the GCD of A and N is equal to 1. So the proof of this is, well, if we're a unit, right? So the forward direction, if A is a unit, we have that A, there exists some B in Z mod NZ, such that A times B is 1 mod N. So that tells us that AB minus NK is equal to 1 for some K in the integers. But what does this say here? Well, we have that an integral combination of A and N equaling 1. So this tells us that the GCD of A and N is equal to 1. Since if it were larger, it would divide left-hand side, so it would also divide 1. So we have an integral combination equaling 1, so that tells us that GCD is 1. Now for the reverse direction, use the extended Euclidean algorithm. So that tells us that there exists some, let's use K and L such that AK plus BL is equal to 1. Namely, AK minus 1 is BL, so A times K is equivalent to 1 modulo L. So we've just shown that so A is a unit. So we've just shown that we're a unit in Z mod NZ if and only if our GCD of A and N is 1. Now, we can finally prove that Z mod PZ is a field, where P is prime. And the proof of this is if A is not equal to 0 in Z mod PZ, then GCD of A and P is equal to 1, because the only elements that the only numbers that divide a prime are 1 in itself. So, and if we note that our system of representatives is 0, 1 to P minus 1, none of these divides P. So that tells us that the GCD of A and P have to be 1. So A is a unit, and we are done. Because a non-zero element being a unit is exactly the definition of a field.